We're now going to look at two very famous and very widespread, widely used examples of affine functions. One is from differential calculus. It's just the Taylor approximation. So that goes back a couple of hundred years. And the second one is a regression model from statistics. We'll start with the Taylor approximation. So in the Taylor approximation, suppose you have a function that the way you'd say this is you maps Rn to R. Now Rn is the set of all n vectors. So the way you should read this notation, which is universally, it's a universal mathematics notation, is this says that f is a function and it takes as an argument or input or however you like to think of it, a vector, an n vector, so n real numbers. And then it returns or evaluates to or gives a single number r back as the result. That's what the second term means. So for example, you might write f of u or something like that, and that would be u here must be an n vector, and f of u is a real number. Okay. All right. So the Taylor approximation is just this. It's the first order Taylor approximation. It says the following, and we're going to develop this near a point z, and it's this. So it's f hat, and the idea of a hat that's common mathematical notation that hints that it's an approximation. So when you see f hat, it's an approximation of f. And that's that notation, or it's just a convention that's common across many areas of applied mathematics. It's not universal. I mean, there's other subfields where hat means something different, like Fourier transform or something. But it's just something to understand is that very commonly a hat means an approximation. Okay, so this says f hat of x. That's my approximation of f, and it's going to be the following function. It's f of z. Now that's a constant. It's just whatever number that is, -2. Plus, and then what we have is a sum of terms. Each one can be interpreted as the approximate change in f due to the change in that component of x or z. So here, for example, x1 minus z1 is the amount you have changed the first component from z1 to x1. And then you multiply that by this partial derivative, the partial derivative of f with respect to x1 evaluated at z. And so you add up all these sort of correction terms and you get this function, and that's f hat. Now, that function is affine. We'll see that momentarily. But the main property of the Taylor expansion is this, is that f hat, this approximation, is very close to f of x when the x's are all near the z's. And a picture will explain that. But very close means not just that they're close, but they're very close, right? Okay. Now we can write out this Taylor approximation using vector notation and inner product. And that looks like this. So this says that f hat of x is equal to f of z. That's a number. Plus, and then up here, if you look at this term, you will recognize it is a sum of products of two things. And if we collect those two things into two vectors, one is just the vector x minus z, and the other one is a vector whose components are these partial derivatives, and that's got a name. So that's called the gradient vector. And so the gradient vector is the set of all partial derivatives of a scalar valued function with respect to x1, x2, x3, up to xn. And this we recognize up here, it's just an inner product. And so we've got this beautiful compact formula that looks like that. And it's kind of nice because it looks like the formula you would have if x and z were scalars. And here this would just be simply f prime of z, which is in fact the gradient when you have just one variable. Okay, now to see that this is an affine function, we could write it a different way. We could write it as the gradient of f, inner product with x, sorry, that's at z, inner product with x. And this, you can think of this as your a, if you like, in the affine model. And then plus, and then the offset. And the offset is going to be f of z minus the gradient of f at z, inner product with z. Okay? And so this part here we would call b. And what that says is that f hat of x has the form inner product of a and x plus b. So, okay. So this is, so The summary of all this is, in fact, you can even think of, a good fraction of derivative calculus is in fact simply, it's an organized method for making affine approximations of functions. So let's see a quick picture. Now the picture I'm drawing is z and x are scalars, so I can draw it. But I'll say a little bit about how this works in the higher dimensional case. So here it is. So here's the curve, which is f of x. So we can see f of x here. And here's a point z. And then this red dashed line is the graph of f hat of x. And you can see it's a line, so it's an affine function. And so what I meant to say earlier when I said it was very close when you're close is if you were to imagine zooming in there, what you would see is that if you moved a little bit from x, like I'll just make up like 0.01, then what would happen is the approximation would be very accurate, like way better than 0.01, like 0.01 squared, right, which is 10 to the minus 4. So that's what this means. So it's tangent to the curve at that point. So this is, and this you know from calculus. Okay, now in higher dimensions, for example in 2, what we would do to visualize this is we would imagine, let's say, a plane and then a surface above it, and that surface would be f. I pick a point z, I go up to the surface, and then what I would have is my graph would be a plane, and it will be the tangent plane. It's the plane that just sort of touches the graph at that point and is actually parallel to it right at that point. And that would be the first order Taylor approximation of the function. Okay, so this is one area of, it's an organized method for producing affine approximations of non-affine functions. Okay, our next example is the regression model. This is essentially a human-made thing because these are just approximate models. But it's absolutely ubiquitous. You may have already heard about this in other courses. I guarantee you will hear about it in other courses. If that's not the case, then, well, you're not taking the right courses. But so it's a very important thing to understand. It's not complicated, but it's super important. And we're going to see it a whole lot later, much more later in this class. Okay, so a regression model is this. And the idea is I have a vector x, and I think of x as a feature vector. So its components are various numbers associated with an item, right? Could be a patient admitted to the emergency room or something like that. It could be it could be a certain each item could correspond to a company on a publicly traded exchange or something like that. And then the entries of x are attributes of that item. So, for example, if it's a patient, you could encode it could be their height, their weight. We could encode their sex as 0 and 1. For, let's say, male and female, we could say are they experiencing chest pain? That could be encoded as 0 or 1, and so on. So that would be these would be attributes of the item, right? For a company, it could be the total capitalization of the company, the last year's return. It could be just various. It could be the sector that the company operates in, or something like that. So okay, so these would be attributes of it. And then y is something that we want to predict, right? And y could be, for example, the number of days that patient will ultimately stay in the hospital, right? Of course, we don't know it because who knows? We have to see how they do and all that kind of stuff. But that's y. We know it after they've left the hospital. And let's say for a company, it could be what is going to be the return on their stock over the next quarter. Is it going to go up 5%? Down 10%? I don't know. We would call that y. Okay? And so what we have is a model, or regression model is like a prediction model. And here's what it is. It's actually relatively straightforward. We're going to look at it. The prediction is an offset v, that's called the offset, plus, and then an inner product of the feature vector with a weight vector or coefficient vector beta. And I'm using some of the traditional notation that you'd see in a regression model. So this is the model, and of course, we could write this out, and it's very important to write it out. So that's like beta 1 x1, right, all the way up to beta n xn plus v. And we can interpret all sorts of things there. Super cool. Like if all the features are 0, our prediction is v. So that's what v is. Oh, and I should say here that y hat is an approximation, supposed to be an approximation or prediction of what y is, right? So y is the true outcome or something like that. So this is useful in cases where you can see x, you don't know why, because maybe it hasn't happened yet or something, because it's something in the future. It's how many days will they stay in the hospital, or what will your return be over the next month. So you don't know it, but you do know x. And so this gives you a way to make a prediction of what that's going to be. Okay, so it's a prediction model. All right, and we can interpret everything very nicely here, right? So for example, beta 1 is the amount by which your prediction goes up when x1 goes up by 1. Okay, so that's kind of the idea. So, and we'll see that in a very specific example I'm going to show you in a minute. So that's the idea. If a beta is, for example, negative, that means that when that feature goes up, your prediction goes down. Okay, so for example, a feature could be, here's a feature, ready? It's x7, and it says, is this a person a heavy smoker? Is 1, 0 means not a heavy smoker. And if y is, if we're trying to predict, let's say, lifespan, then I would hope that beta 7 is negative. And what that means is that, anyway, a good model would have beta 7 negative. And that means that if you're a heavy smoker, our prediction of your lifetime is going to go down. In fact, quite literally, beta 7, which is negative, is going to be the number of years our model predicts you will lose in your lifespan if you're a heavy smoker. Okay, so we'll come back. We're going to be talking about this in great detail later. This is just your first introduction. But the main point is this. That is an affine function of the features. That's it. It's linear plus a constant. Okay, so that's the idea of a regression model. I'll just give you a quick example, and like I said, we're going to come back to this and look at this in much more detail later. So here's an example, just to sort of get in your head how this might work. So let's say y is the selling house, is the selling price of a house. It's how much it sells for, and let's say it's in thousands of dollars. So 230 means it's sold for $230,000. Okay, and that's in some location over some time period, right? And the regressor is going to be extremely simple. It's going to have, the feature vector is going to have just two features, right? And it's going to be the house area is number 1, and the house area we're going to give in thousands of square feet. So 1,000 square foot house is a 1, and bedrooms is going to be, of course, just the integer. So for example, 2.1 comma 3, that's a 2,100 square foot house with 3 bedrooms, just for example. Okay. Now, I should add, this is an embarrassingly simple example. No one would predict a house price based on 2 features, right? Real ones like Zillow or Trulia, they would actually predict a house price based on tens or hundreds of features, right? So, but nevertheless, it gives you a rough idea of what it's going to look like. Okay, and so here's a regression model. Right now, I cannot tell you where this regression model came from, but that's not the point. Right now, just to understand what it says. Super interesting. It says that beta is 148.73 and minus 18.85. And the offset is 54.4. Okay. Now, by the way, later in the course, you will be able to fit regression models to data. But for right now, it's important to understand just what a regression model is. What does it say? And it's actually really cool. Let's talk about it for a second here. This first one we can interpret in a beautiful way. It says that basically for every 1,000 square feet of increase in house size, our model predicts that the selling price is going to go up by about 150,000. Okay? So, I mean, you could even sort of divide it and say, well, it's, whatever it is, it's $1,500 whatever dollars per square foot, or however it works out, right? Something like that, right? So that's an interpretation there. Now, this one, that's tricky to, it looks strange, right? It says, wait a minute, this is weird. This says that when the number of bedrooms goes up, we predict the house price to go down, okay? So, then you think that surely that's wrong. And you go, well, it might not be wrong. I'll give a rough explanation for it now. this says that if the number of bedrooms goes up, but the house area stays the same, then in fact the price, our prediction of the price goes down a little bit, and you could chalk this up, or if someone asked you why, you could say, I don't know, maybe it's more crowded or cramped, right? If you have a 1,200 square foot house and I add another bedroom, yeah, it's too cramped or something like that. I'm just making this up. Also, it's probably a good idea not to get too. I mean, you can think about the model, but don't take it too seriously. Okay, so this is this would be the idea. Oh, this offset, that's 54.4 thousand. You can give kind of an approximate interpretation goes like this. You would say that that's actually the cost of the lot, because it's actually, that is our prediction of the selling price of a house whose feature is 0, 0. But that's a house with 0 square footage and 0 square footage and no bedrooms, right? So in other words, known as not a house. So I mean, I wouldn't take any of this too seriously, but if you wanted to interpret this, you could certainly interpret it that way, that's the price of the land or the base price or something like that. Okay, so that's a regression model. And let's just look at a quick example of how you might use that regression model. Well, I've shown you this is 5 houses, okay? And actually the houses we selected, actually the first one has 1 bedroom, then 2, 3, 4, and 5 houses, okay? But doesn't have to. And then what I'm going to give you, by the way, this is actually some real data. It doesn't matter. But here, the first one is 846 square feet. We can see that here. This 5 bedroom house, that's 39. That's almost 4,000 square feet. Okay. So here, what's listed here is what the actual price the house sold for. Okay. And then over here, that's our regression model prediction. Now, by the way, if we know how much the house sold for, you definitely do not need a regression model, because if someone says, what do you think it's going to sell for? You'd say it just sold. And as a matter of fact, it just sold for 234.5K, period, right? So you don't need a prediction model. You need the prediction model before that, when you'd say, hey, how much do you imagine this house is going to sell for when it does? And that's our prediction. And you can look at these two and you can just eyeball them. And, this kind of makes sense. You can see we're getting the flavor of it, right? I mean, we do predict that, for example, that sells for a whole lot more than that. We make some pretty good predictions, right? Like that's a pretty good one. That's not such a great one right there. That's not fantastic. That's, okay. And that's not so great, really, that last one, that first one. I mean, this is silly because, we're attempting to, I mean, it's not unexpected. We're attempting to predict the price a house sells for based on 2 attributes and nothing else. That's ridiculous because, in fact, it's going to depend on at least 50 attributes, like how good are the schools in this neighborhood? How much of other houses in the same neighborhood sold for? Things like that. So there's a lot more going. And at the end of the day, by the way, what the house price is it is precisely the amount somebody somewhere decides to pay for it. And it obviously has much more to do than even the 50 parameters that, let's say, one of these other commercial house price, sale price guessing companies would use, right? It depends on who falls in love with the house. It's 2 blocks from your cousin. Or whatever, or some good friends. I mean, so there's lots of other things that determine that. But the main idea here is it's just an approximation, and it's an affine approximation. Okay. And here would be, and we'll get to this later, but I think this is a scatter plot of maybe 500-600 houses from a certain area over a certain time period. And what we're plotting here is these are sales that actually happened. So in some sense, this axis, the x-axis, that's real. That's like it closed. We went to the county assessor's office or whatever it is, and this is you can get the official amount that changed hands to buy the house, right? On this axis, what we're doing is we're gonna predict our regression model. Now, our regression model is pathetically simple, right? It uses 2 regressors and all sorts of other stuff. And if our prediction model were perfect, everything would be on this diagonal line, the x equals y line. Everything would be there because it just means basically that our prediction and the actual price were exactly consistent, right? So that's not the case, but you can see that, a lot of them they're kind of concentrated towards the line. You can see a couple things. For example, here's some examples of ones where we do an absolutely, truly terrible job of predicting, right? So, I mean, these are just terrible jobs. This is an example of that of something that sold for 700,000, and our prediction was like 300,000. I mean, we were off by a factor of two, right? On the other hand, we have a bunch of houses where we did pretty well. So anyway, so this is just your first exposure to regression model. If you haven't seen it in other classes, main takeaway here is it is an affine function. So it's an example of an affine function.